We see them everywhere, the titans of modern construction, steel and concrete. They are the very definition of strength, the bedrock upon which our cities are built. When you look at a towering skyscraper or a sprawling bridge, it's natural to feel a sense of security, to believe that the sheer power of these materials guarantees safety. But what if I told you that this belief, this fundamental assumption that stronger materials automatically equal a safer building, is one of the most dangerous myths in engineering? What if the biggest, beefiest beam isn't always the best? It's time to think again. This misconception is incredibly common, and frankly, it's understandable. We're wired to think that more is better. A thicker rope is stronger than a thin one. A heavier shield offers more protection. So, it follows that a building made with the highest grade steel and the densest concrete must be invincible, right? We imagine a structure as a collection of powerful, independent parts. We focus on the impressive specifications, the tensile strength of steel, the compressive strength of concrete, and we tick a mental box labeled safe. This is the brute force approach to construction, a philosophy that prioritizes raw material power above all else. But a building isn't a simple object. It's a complex, interconnected system, and in that complexity lies a hidden truth. The reality is that a building's safety has far less to do with the individual strength of its materials and everything to do with how those materials are designed, detailed, and connected to work together as a unified whole. A chain is only as strong as its weakest link, and in construction, those links are the connections, the foundations, and the invisible pathways through which forces travel. An incredibly strong beam is useless if it's connected to a column that can't handle the load. A massive foundation is worthless if the soil beneath it gives way. It's the intelligence of the design, the precision of the execution, and the understanding of the entire system that truly creates a safe structure. In the coming minutes, we'll explore real-world examples where overlooking these principles led to catastrophic failures, not because the materials were weak, but because the design was flawed. We'll see how the smartest engineers don't just ask, "How strong is this material?" but "How does this entire system behave under pressure?" Most people assume using the strongest materials guarantees safety. In reality, poor design can make even the strongest materials fail. Take, for example, the sobering history of building failures. When we analyze these events, a surprising pattern emerges. More often than not, the culprit isn't weak or faulty materials. The steel beams were strong, the concrete was mixed to specification. The failure was rooted in something far more fundamental, the design. A building isn't just a collection of strong parts, it's an intricate, interconnected system. Think of it like a human body. Having the strongest bones in the world won't help if your joints are designed improperly. In construction, the joints are the connections. The load paths are the circulatory system for forces, and the architectural and structural plans are the DNA that dictates how everything works together. When that DNA has a flaw, even the most robust materials can be rendered useless. To see this principle in action, let's examine one of the most critical failure points in modern construction, the beam-to-column connection. Imagine a state-of-the-art high-rise, built with high-strength steel. The beams and columns themselves can withstand immense forces, but the true test of the structure lies where these elements meet. This connection is responsible for transferring massive loads, from the building's own weight to the force of wind, from the horizontal beams to the vertical columns, and ultimately down to the foundation. Now, what happens if the design of this connection is flawed? Perhaps the engineers didn't account for the slight rotation a beam undergoes when it bends. Maybe the welding specifications were inadequate, or the bolt arrangement created unforeseen stress points. In this scenario, the immense strength of the steel beam is irrelevant. The force, instead of being smoothly distributed, becomes dangerously concentrated on a few weak points. It's like trying to stop a car by grabbing a single spoke on the wheel instead of applying the brakes evenly. A tiny crack can form. Under continued stress, that crack propagates, leading to a sudden, brittle failure of the connection. The beam detaches. This single localized failure can then trigger a catastrophic chain reaction known as progressive collapse, where the load from the failed section is suddenly transferred to adjacent members, which in turn are not designed to handle it. One failure leads to the next, like a row of dominoes. The building's strength wasn't in its materials but in its design. and in this case, the design failed. Engineers balance load paths, soil conditions, and design, not just materials. So, if simply using bigger beams and stronger steel isn't the silver bullet for a safe building, what is? Where does true structural resilience come from? The truth is, strength comes from a sophisticated partnership between proper design and precise execution. It's not about the brute force of the materials themselves, but the intelligence with which they are assembled. Think of a building not as a collection of individual, strong parts, but as a single, integrated system. A complex web where every single component has a critical role to play. A skyscraper-grade steel beam is rendered completely useless if the connection holding it in place is poorly conceived or improperly installed. The entire system is only as strong as its weakest link. This is where the art and science of structural engineering truly come to life. An engineer's most crucial task is to create a clear and continuous load path. Imagine it as a carefully planned highway for immense forces. Gravity, wind, people, and even potential seismic shocks are all loads that need to be safely collected and channeled from the top of the building down through its skeleton and harmlessly into the earth. A flaw in this path, a weak connection, a missing brace, or an undersized bolt, creates a structural dead end. The force has nowhere to go, and it builds up until a component fails, potentially triggering a cascade of failures throughout the structure. It's like having the world's most powerful engine in a car, but connecting it to the wheels with a plastic transmission. The power is there, but it can't be effectively transferred. In a building, the design is the engine, but the on-site execution, the quality of the workmanship, is the transmission. Even a flawless design can be fatally undermined by poor craftsmanship, unapproved material substitutions, or a simple failure to follow the plans. This is why quality control, rigorous inspections, and skilled labor aren't just line items on a budget, they are fundamental pillars of safety. The key lesson is that strength is born from the intelligence of its design and the precision of its construction. History has shown us time and again that overlooking this principle has devastating consequences. If you're a property owner, always hire qualified engineers, not just builders. Stronger buildings come from smart engineering. Subscribe for more myths busted.